You ever see one of those colossal container ships stacked stories high with cargo and just think to yourself, how in the world does that thing not just fall over? I mean, it seems like it completely defies logic. Well, today we're going to dive into the incredible physics that keep these giants floating upright and perfectly balanced. And it's a great question, right? It looks like it should be totally unstable, but it all comes down to some really precise calculated science. And trust me, by the end of this, you'll be able to look at any ship and see the invisible forces at play that are keeping it safe. So, at the very heart of all this, you have to picture a constant tug of war. It's happening every single second of every single day. It's this dynamic duel between two massive, powerful forces, and they're always at work, even on the calmest seas. And that's really it. That's the core conflict. You've got gravity, which is the total weight of the ship, always trying to pull it down into the water. And then you have buoyancy, the force of the water itself, pushing right back up. How a ship manages this fight is the secret to what's called transverse stability, which is just a fancy way of saying its ability to not roll over sideways. Okay, so to really crack this code, we just need to learn a simple four-letter alphabet. If you can understand these 4 points, K, B, G, and M, and how they relate to each other, you've pretty much mastered the entire concept. Think of them as the main characters in this story. All right, first up is K, for keel. This one's the easy one. It's just the very, very bottom of the ship. Think of it as ground zero, our starting line. Every measurement we take from here on out starts at K and goes up. Simple as that. Next up, we've got B, the center of buoyancy. Now here's where things get a little more interesting, because B is a moving target. See, as a ship rolls in the waves, the shape of the part that's underwater is constantly changing. Well, B is just the geometric center of that underwater shape, so it moves along with the roll. It's the exact point where all that upward force from the water is concentrated. And working against B, you've got G, the center of gravity. The best way to picture G is to imagine taking the entire weight of the ship, the steel, the cargo, the crew, the fuel, everything, and concentrating it all down into a single tiny point. That's G. And its only job is to pull straight down. And unlike B, G only moves when you physically shift weight around, like loading new cargo or burning off fuel. And finally, we have the most abstract, but maybe the most important letter, M, for meta center. Okay, stay with me here. The easiest way to think of M is as an invisible hinge, floating in the air high above the ship. As the ship rolls side to side, the whole thing is basically pivoting around this imaginary point. And where M is located is absolutely critical, because its relationship with G, well, that's the whole secret. So you see, it's not about any one of these letters by itself. It's all about the relationship between two of them. In fact, you could say that the entire safety of a multi-million-dollar ship and its crew boils down to just a single measurement, one number that every single ship's officer lives and breathes by. And that number is GM, also known as the metacentric height. All it is the vertical distance between G, our center of gravity, and M, that imaginary hinge. Just think of GM as the ship's safety margin. The bigger the GM, the more eager the ship is to snap itself back upright after a wave hits it. It's a direct measure of its will to stay stable. So here are the rules of the road. It's pretty simple. If G is below M, you have a positive GM. That's good. Physics creates a powerful force that pulls the ship back upright. You're safe. Now, if G and M are at the exact same height, your GM is 0. That's very risky. The ship gets lazy, it'll roll to one side and just stay there. Not good. But if G ever rises above M, you get a negative GM, and that is catastrophic. The forces actually flip, and they will actively work to capsize the ship. Okay, enough with the theory. Let's see how this works in the real world. Let's imagine we're on a ship and the crew needs to move one heavy piece of machinery. We're about to see how a single action can dramatically alter the physics of the entire vessel. All right, here's our ship. She's a 10,000-tonner. Now, don't worry about all the numbers, just focus on two of them. The starting height of our center of gravity, kg, is 5 meters, and the height of our metacenter, km, is a bit higher at 6.5 meters. The plan is to lift a 200-ton block of machinery 6 meters straight up. So what do you think is going to happen? So before we touch anything, let's calculate our starting safety margin. We just take the height of the metacenter, 6.5 meters, and subtract the height of gravity, 5.0 meters. That gives us a starting GM of 1.5 meters. That is a solid, healthy safety margin. Right now, this is a very stable ship. Okay, now the lift begins. And just think about it intuitively for a second. If you take a heavy part of any object and move it higher, the whole object's center of balance has to move up a little bit too, right? Well, the math shows that this one move has pulled the entire ship's center of gravity up by 0.12 meters. Our new kg is now 5.12 meters. So what does that do to our safety margin? Let's run the numbers one more time. The metacenter height hasn't changed, it's still at 6.5. But now we subtract our new higher center of gravity, which is 5.12. And our new GM, our new safety margin, is 1.38 meters. So look at what just happened. By just moving one piece of weight higher up, we raised the ship's overall center of gravity. And that action literally squeezed the gap between G and M. It shrunk our safety margin. The ship is now, quantifiably, less stable than it was just a few minutes ago. So we've seen how moving weight up and down affects stability. But that's really only half the battle. What happens if you move that same weight sideways? Well, that's what causes a ship to list, to develop a permanent and potentially very dangerous lean. Now, there's a formula for it, but don't sweat the math. The key thing to understand is that the angle of that lean comes down to two things: how far off center the weight is shifted, and our old friend GM. A ship with a big GM is called stiff. It has a ton of power to resist leaning. But a ship with a small GM, like the one we just made, is called tender. For a tender ship, the exact same sideways weight shift will cause it to lean over at a much, much more dramatic angle. You know, the biggest thing to take away from all of this is that a ship's stability is never a fixed number. It's a living, breathing thing. Every container that gets loaded, every gallon of fuel that gets burned, it all changes the location of G. And that means the critical safety margin, GM, is constantly in flux. A huge part of being a ship's officer is being a master of gravity, constantly managing G to maintain a safe GM from the moment you leave port to the moment you arrive. So that leaves us with this final thought. The next time you see one of those massive ships piled high with cargo, you'll know exactly what's happening beneath the surface. With every single box they stack higher, you'll know that its center of gravity, G, is rising. And with every inch that G rises, that critical stability margin, that GM, is shrinking. You'll see it for what it truly is: a constant, delicate balancing act between the demands of global trade and the unforgiving laws of physics.